In this section, we show some of the benefits of using matrices when we work with regression models. So the way to write the model down, the way we have written it down so far in the chapter, is like this, where you have each value of y at time t is some function of the values of all of the x variables at time t plus an error term. Now, if we write all of the y's as a single vector like this, so this is all of the observed response variables from one up to time t, and we call that boldface y. And we do the same with the errors, the epsilons, and we do the same with the betas, all of the coefficients here. So each of them is written as a vector, and then all of the x's we write as a matrix, where the first column is all ones, the second column is the value of the first predictor for each time, the next column is the value of the second predictor for each time, and so on. And once we write those vectors and matrices, we can then simply write the all of the regression terms that look like this, the regression equations, we can write in a single line like this. So that's for all time t. So it's very simple, and it gives us a way of solving things with regression that's not really possible if you work with the subscript variant at the top of the screen. For example, you can immediately write down the estimate for least squares estimate of the coefficient. So y minus x beta gives us the error, and transpose that and times itself gives us the sum of squared errors. So minimizing the sum of squared errors, we can just use some matrix calculus. So we differentiate that expression with respect to beta, and you can derive the optimal beta as this expression here, x prime x inverse times x prime y. So really simple equation, closed form solution as possible when we use this matrix way of writing the equations down. That's known as the normal equation. It gives us the value of all of the coefficients once we can express the predictors and as the matrix x and the response variable as the vector y. Also means we can write down a simple expression for the estimated variance of the residuals based on the sum of these squared errors, y minus x times beta hat. Also gives us a way of seeing why the dummy variable trap's a problem, and in fact any multicollinearity is potentially a problem, because if you fall for the dummy variable trap, or if you have some exactly collinear predictors, then this x prime x matrix is then singular, and so you can't invert it. If we are willing to assume that the errors from our regression are independent and identically distributed and that they're normal, then we can write down the response y as this expression here, a normal expression with this is your multivariate mean and this is the multivariate variance. And then you can write down the likelihood just using the expression for multivariate normal distribution, and we get this expression like this. And then you maximize the likelihood by minimizing the stuff that's over here, and that demonstrates that maximum likelihood estimation is exactly the same as ordinary least squares in the context of regression with normal errors. So you get a lot of things. You can do a lot of things once you adopt the matrix formulation. One of the really cool things is to do with cross-validation. So first of all, let's write down what the fitted values look like. So the fitted values are the predictions in sample. So our predictors in sample are in the matrix X. So if we multiply that by the estimated betas, we get the predictions for each Y in the training data. Then we replace the beta hat by using the normal equation that we just saw by that expression. And then we get Y hat is equal to x times x prime x inverse times x prime y. And if we then combine all of the part of the expression that involves the X matrix, we can write it as this matrix H times Y, where H is equal to X times X prime X inverse times X prime. And that's called the hat matrix because it turns your y's into y hats. Now, the cool bit is this, that we can actually compute the leave one out cross-validation mean squared error directly from the model fitted to all of the data without actually having to refit lots of times. And that we do that using the hat matrix. So if we take the diagonals of this hat matrix and we call those H1 up to HT, and we take the residuals from the fitted model, that's y minus x times beta hat, then the cross-validation statistic can be written like this, where each residual is divided by 1 minus the corresponding diagonal on the hat matrix. And that's amazing because we're actually calculating the error between what we saw and what we predicted we would see using all of the other data, but not including that observation. So it's like you'd fitted, if you've got T observations, it's like you fitted T separate regressions, each one leaving out one of the observations and predicting the one that you've left out. But you don't have to do that. You can just do it with one single fit and then use this expression. So it's very cool, and it's why we can do leave one out cross-validation so quickly in a regression context. The last thing I wanted to show you was how to write down the forecasts and the forecast variance in this matrix form. So your forecasts can be written as this expectation, where y is your observed response variable, x is the matrix, which contains all of the predictor variables, and x star, it's a new thing here, that's a vector, a row vector, containing the values of the predictors for the period that you're forecasting ahead. If you're forecasting one period ahead, if you're forecasting lots of periods ahead, then it's a matrix where each row corresponds to one of those periods. And then, so we assume we know all of the y's and x's in sample and that we know the x's in the test set, in the test period, the forecast period. And then you can write that down as just x star times beta hat, or this here, where we just replace the beta hat by its estimate. So that's the point forecasts of y hats in the future periods. The forecast variance can be done in a similar way, where it's y star given the values of x and x star. And that is like this, where you've got sigma squared, which is the estimated variance for the residuals, times 1 plus this expression. Now the 1 gives you the variance contributed by the error term in the model, and this part gives you the variance contributed by the uncertainty in the estimated coefficients. So unlike other models in forecasting where we sometimes assume that the model is estimated exactly correctly, and we don't worry about the uncertainty in the parameter estimates, in regression, we can easily put in the uncertainty in the parameter estimates using this equation, and that gives us the forecast variance. That is, of course, assuming we know x star, we know the future values of the predictors. If you don't know the future values of the predictors and you're having to estimate them, then this variance expression will not take that into account. And once you get the variance, you can easily get prediction intervals. For example, 95% prediction intervals can be computed in the usual way, plus or minus 1.96 times the square root of the variance.